So welcome to this pre-recording of lecture 16 of Introduction to Symbolic Computation. This is the review for the first midterm exam scheduled to happen on Wednesday, 6 July. So I will first explain how this midterm will happen, and then I will give an overview of what we have covered so far. So we are 15 lectures in, so this is the 16th lecture or the 8th session in the summer. And after the slides, I will present sample questions, so representative questions for what we have covered, with an emphasis of some topics that perhaps should have received more attention. So in a way, this review represents representative questions, but certainly not exclusive. So you must review the 3 quizzes we had, and you also must look at the homework problems. Okay, so this is an online course. So you will receive questions by email shortly before noon on Wednesday, 6 July. But before that to happen, you must email me before noon on Tuesday, 5 July, that you commit to taking the exam. So without doing this action, you will not receive the questions, and by default you will then skip the exam. So that's the default. So the exam has to be solved with Sage in a Jupyter notebook. So this course is obviously open book, open notes, open computer. The main restriction is that you, of course, solve the exam individually. In order to ensure this individuality, I will have sufficiently many multiple versions of the questions available. So, as with the quiz, you must upload your answers in one single Jupyter notebook before 1:40 on the same day of the exam. Okay, there is the skipping policy. By default, if you do not do anything, there is the automatic skip. And there might be very good reasons to skip the midterm exam. This course has been running very fast, perhaps too fast for you. And you may wait a little bit till you gain more experience with the course materials. So for that to happen, you do not need to do anything. Note that 5 July at noon is also the deadline for a homework submission. If you have not submitted any homework so far, then I would perhaps urge you to consider either to really start working on homework, or consider even skipping the midterm exam. So anyway, if you skip the midterm exam, no harm done. Your final, who now counts for 200 out of 700, will then count for 300 out of the 700 points. So the final is mandatory to pass the course. Without taking the final, you will not pass the course. But you can transfer even more weight to the final exam by not taking the midterm. And there might be good reasons for doing that. Now, if you have committed to seeing the questions, if you have received the questions, but if you do not submit your answers in time, then you will receive 0 out of 100. So the other thing is that skipping policy is something that is done during the exam. If you have a disappointing score, then you cannot ask to drop the score. So then your score actually counts. So what I want to indicate here with the skipping policy is that do not take the exam just because it's something that you feel that you should be doing. Of course, you should be doing it, but if you're not prepared, if this would be your first uh, activity in the course, then you may be setting yourself up for disappointment. Practice, 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 and as I will have, as I said in the beginning of the course, the most important resources that you make are your own Jupyter notebooks that you make during uh, this course. If you have not touched, if you have not done much on that front, then it might not be that going that well. Okay, so there are two parts in the midterm exam. So the first part was actually most extensive. So we have 8 sessions. 5 of those 8, or the first 10 lectures, cover the first part. So by now you should be very familiar with the Jupyter notebook, certainly knowing when to use code cells and markdown cells. Running Sage Math should also be already something that starts to go well, either if you do it on your own computer or you do it in the cloud with CoCalc. So that's actually the first step that we have continued through so far all sessions. So we have seen approximations for symbols, exact ones using rational numbers and floating point numbers. We have covered algebraic numbers, which you have already seen. Complex numbers are a special type of algebraic numbers in some way. We can do this over the algebraic numbers or over finite fields. There are some computer science aspects, so symbolic computation is kind of between computer science and mathematics. We have seen how to use functions to store data, so we can, and that actually applies the referencing to objects. We've seen binary expression trees when we are looking into fast callable objects. Speaking of fast, Python has a reputation for being slow, but with vectorization and Cython, we can significantly speed up the computations. So I probably have omitted several details in this bulleted summary of the first part, but this is somehow the essence of what we have covered in the first part, with a focus on numbers, if you like. Then we looked into polynomials and expression, knowing that algebraic numbers kind of make the connection between the numbers from the first step, from the first part, with the symbolic factorization. Note that there is an important distinction between a general expression and a polynomial. We've seen polynomials in one variable, rational polynomials or quotients of polynomials, and polynomials in several variables. General expression trees are not binary. Substitution, expansion, and factorization, here now spelled correctly. These are the three main tools to manipulate expressions. And normal forms are important to decide whether two complicated expressions are the same. So this is an overview of the first two parts of the course. Again, the most important action part is that if you do not do anything, uh, if you do not study, then you will skip the exam automatically. So often I have frantic questions kind of at the very early start. So if you send me an email by 12 noon, on 12 noon, where are the questions? I want to do the midterm exam. Well, if you have not signed up, if that's the only time when you realize that there is an exam at noon on Wednesday, 6th July, you will be too late. So without signing up before noon on Tuesday, 5 July, you will not receive the questions and you will skip the exam. So by that I want to enforce that at least 24 hours before the exam you do something. You commit to taking the exam. Okay, let me now switch to the Jupyter notebook. So I have two Jupyter notebooks prepared. So the first notebook is a notebook with questions. So the format in which you will be receiving the questions will also be a Jupyter notebook. And that is convenient, so you can answer the questions. You can use that same notebook to submit your answers. Also, from a pure pedagogical perspective, I will post this Jupyter notebook. One good way to prepare for the midterm exam would be to take this Jupyter notebook and to try to solve these questions. So there are 8 representative questions. Try to solve these questions on your own in kind of 100 minutes, like you would be taking the midterm exam without looking to the answers. So what I will do now in the remaining half hour or 35 minutes, I will scroll through the answers. So I have 8 questions, and these 8 questions, solving them for me in 30 minutes might be also a little bit, but doing all the talking might be a little bit too ambitious for me. It's also late in the evening. So I will scroll through the answers. So I have another Jupyter notebook prepared, um, where I will give immediately the answer. So in some sense, in the real preparation for an actual midterm exam, that might not be the best thing to do, because the questions that you will receive will actually be different, but very much related. Okay, let's look at the first question. So we look at the square root of 2, and we want a nearby rational approximation where for S, capital S is actually a symbol. At some point I said this was an unevaluated function, where with the nearby rational approximation we can bound the size of the denominator, not larger than 1000. And so that's the first question, nearby rational approximations. The second question is then on constructing a sequence of nearby rational approximations that get larger and larger. And then in the third part, we verify the accuracy of the rational approximation. Now, we've seen 2 other types of rational approximations. So we've seen the rational approximations with prescribed accuracy, and I think the first quiz was on that. I also spent some time on giving examples on convergence. So if you use the convergence of the continued fraction, then you should not be using nearby rational approximations. Or if you see rational approximations with prescribed accuracy, then you should not be using nearby rational approximations. So here I'm giving you one sample, but there will be at least three different versions of the midterm exam. So I'm giving you two other versions for which we have seen the um, for which we have seen questions. So by the way, and perhaps I should have done this earlier. So how do you actually study for this course? Well, there are the lecture notes, and the lecture notes have other questions here. So I have the review, and this should still be the review of the first 15 lectures. But then I have sample exams. So this gives you more questions and also more answers. So you could also, but keep in mind that with past runs, so this was in a regular semester, uh, students only had 50 minutes, and the size of the exam was also a little bit shorter. So the exam that you will be getting will be larger. I will be giving you at least 8 questions because you have 100 minutes. But these are other very good questions, and on the websites, on the previous website for these runs, I also have the answers there. Okay, I've explained the first question. So here is one way to answer this. So you define the symbol, and then you look for the nearby rational approximation. So there are several things that can go wrong here, even if you know the nearby rational command still. You have to know the bound. So actually, you can also bound the numerator. That could be an alternative question as well. You must convert to a floating point approximation because this nearby rational operates on a floating point approximation. So here you see indeed that the numerator is less than, that the denominator is less than 1000. Now, list comprehensions are very powerful in Python. If you took a Python course, then you must certainly have seen many examples of this. I tried in the first steps of the course also explain the list comprehension construct. There is a catch here. We go all the way to denominators of size 10 to the power 10, which is already quite large. And in order to observe the the accuracy, so these numbers get larger and larger, but also the hop in accuracy actually goes past the RR. So we have seen that the RR is 53 bits. Here I double the precision to 100 bits. Otherwise, you will not compute the number of correct decimal places. So, in essence, you will get already a lot of credit if you know how to use the nearby rational command, correct? If you know the list comprehension, so much better. But then there are the issues with setting the precision. Um, so you will see that if you do not do the setting of the precision, that you will see here 16, 16, 16. So the 16 decimal places is about the 53 bits. Okay, so in studying and preparing for this test, please now also review the two alternatives. Um, the prescribed accuracy and the convergence of the continued fraction. So let me go to the next question. So the next question is a question that's more programming like. Um, it's concept that we have discussed in the lectures, um, and we will see this also in greater detail in the second part. We will see an application of this for the member tables. In a way, this is a very good review question. What is the question asking? It's asking for a function that stores definitions. So it is a what is. So what is computer algebra? Now, if you do this the first time, the function doesn't know it yet. So you have to tell it. So call it again with the definition. So the definition of computer algebra is the study of algorithms in symbolic computation. That was the second definition that we saw. So the first definition is what is symbolic computation. So you see, so these are three calls with the function, and this function will store the definition of computer algebra. So the next time, so the third time actually, after you have defined what computer algebra is, you will see the correct definition. Now, this course requires computer literacy. If you are an MCS student, then you should actually have no problems with this. In a way, if Python was not your first programming language, then you must know how to work. So I will review then how you can work with the default optional arguments. You can see you can call it with one argument, but you can also call it with two arguments. We've seen dictionaries when we did the substitution, the subs command. So here is the definition. So the what is function is defined, takes three arguments. So the user always must provide the name. That's here in the example computer algebra, and optionally a definition. So if in any case the lookup will happen. So if the name belongs to the dictionary, and that is in Python very nicely defined. If the name is in the dictionary, is one of the keys, then it will actually print out the corresponding definition, whatever is stored there. Now you can check if the definition is there or not. So now if there is no, so the call again message is given if the definition is not there. So the definition is preceded by a star. So definition is a word that I used, so it's not a reserved keyword. There are many correct solutions to this. And this is a tuple. So if if nothing is in the tuple, then it will actually print a call again with the definition for the name. So that's actually the second clause here. That's the first call. The second call, the tuple is there, and then you select the first element of the tuple, which gives you the definition string. Okay, if Python was not so familiar with you, then, or if it's a long time that you have seen Python, then this is actually a bit a scary question. But I think it's kind of an excellent review question, because you could actually use this function to look at the course conceptually. So we've seen many definitions of concepts. So for example, expression swell. What is expression swell? What is normal form? Um, what is lexicographical order? All terms that you kind of would need to know. Um, so you can practice with this. So that's the second question. So the third question is on algebraic numbers, and I can display this so that the answer is not yet visible, so I can indicate. So here is the question. So we have a polynomial of degree 4 over the field of bits of the modulo 2 integers. Does this polynomial factor? If so, what are the factors? And if it factors, does it factor into linear as a product of linear factors? So the answer to question 1 will be most likely that there will be nonlinear factors, so factors of degree higher than 1. Otherwise, part 2 wouldn't make any sense. So create then the field extension and write the factorization of the polynomial over this extended field. Okay, so how does the solution or a solution go? So what you see here is the reset. So it might actually be a good practice to start all your answers with reset. So you can solve the question on the exam in any order. If you start always with a reset, then you can use the variable. So x is commonly used. So we will use x sometimes as a variable in an expression. And here it is used as the variable of polynomials over the Galois field 2. So that's the short way to define the modulo 2 integers. So we've seen other ways to do this, and they are equally good as well. So we define our polynomial, and then I phrase the question, is that polynomial irreducible? And the answer is no. It gives false. So it has factors. So I write here one sentence to make sure that you can correctly interpret the answer. It's also actually good for you to do this. Try to, I'm saying this in my own words, but if you can say it in your own words, then it's good that you demonstrate that you understand what is going on. So Sage might not always be collaborating with you. You may get stuck in the technicalities. But if you can explain what goes on in words in a markdown cell, then that will give already you partial credit. Okay, what happens with this polynomial is that indeed it factors, and you see that it's a polynomial of degree 2, and it factors because it's twice that polynomial. So the polynomial is actually a square. And to define the field extension, I need the irreducible factor. So I will select the list of factors. Okay, so now comes the critical part. So you can eventually also retype it. But know again that retyping is not really that clean. We throw away the multiplicity here. So with tuple assignments in Python, there are actually cleaner ways to do this. Then comes the critical instruction. So the critical instruction is over here, where you have your right hand side. which is typically defined by the context. So, what is the name of your irreducible polynomial? Perhaps you can actually split off this statement here, the f, to make sure that you have selected the x squared plus x plus 1 correctly. And you also have the coefficient field here, the modulo 2 integers, where you started with. Could be the rationals. So we have, so there will be many. So I think you had a quiz on extending the rational numbers. So the reason why I put here the finite field extension might be because we have seen finite field extensions a little bit later, after algebraic numbers even, when I discussed lookup tables. Um, so by the way, it's now a finite field. So I forgot to explain. So you then must come up with the name of the extended field. I use K. You must come up with a name for the symbol of the root that you add. So I use R. We sometimes use A. X is not a good name because X is the letter, the symbol that you use in your polynomial. X is not a good name. Uh, Also, if you have already used L for your list, don't use your L here again, or please use a name that you haven't used yet. This is a finite field. You can be asked how many elements are there. So 2 to the power 2. So we started with a field of size 2 and we used an irreducible polynomial of degree 2 to extend. So there are alternative versions of the exam. So I, instead of asking give the factorization, explain the size of the field, or give one element in this field, to give the root of this field to the power 5 and explain why this simplifies to a polynomial in R of degree 1 in this case. Okay, so the third question, to see the factorization, requires a cast of the polynomial that needed factoring into this extended field. Now it looks like this is still not really a factorization in linears, because we would expect 4 factors, but there are actually 4 factors, but they appear with multiplicity 2. So we have fully factored the polynomial. Okay, let me move on to the next question. This is about vectorization. So Python has, not entirely undeserved, the reputation of being slow. That's mainly because it is interpreted, and that means that Python needs to figure out, uh, depending on the context, what types are being used. Um, and it's also a rapid prototyping, so it's mainly convenient to try out something. But through vectorization, Python is still very suitable, and consequently also the numerical routines that we would be using in SageMath. So you can still write very efficient Python code. Still Python code, but reorganize it using the vectors that we have from NumPy. Okay, so we have a Python sum, and essentially this will be a one-liner, although you may want to do this step by step. So I remember when I first introduced this, again, if Python was not your first programming language, um, it's good to work with the list comprehension first and do this for small values of n, and then do the sum, then do the multiplication by pi over n, and then do the floating point conversion. So I'm giving you immediately the answer, which is not so well best preparation, but here it is. And also immediately with the vector, with the verification. So this is an approximation for a definite integral. We are not yet into integration, but summing something that we can do. You're not, a documentation string is not mandatory, but it's an opportunity to put a documentation string in there to, for you to show if something goes wrong, that somehow you understood what you were doing. So part of the difficulty in this course is to translate the mathematical symbols into code that can be executed. So if you say, I'm returning here the sum of this, you are already parsing this statement. So you see the for loop. So here, remember the range, it ends at n minus 1. So here, very conveniently, we can write n. So starting at 1, ending at n minus 1. So this is kind of an advertisement for Python as well. So it takes one line, so I will not show the LaTeX, but you can look at the LaTeX code. So typing up the LaTeX is almost as complicated as typing the Python code. So this is a review problem. On an exam, I might actually give you the hint that this is an approximation for 2. So here you see 1.999. It's a very slowly converging sum. So that's the Python version. For the NumPy version, we need the vectors. And one way to construct a vector is to work with the A range. So even for myself, I had to practice this a little bit. So here I could have stated everything in one statement, but I separated it. So here you see we at the lecture over NumPy vectorization, I illustrated also the A range. So what A range does, it gives a list, or actually an array here. So the reason why this will go faster is that we work with arrays instead of lists. Arrays are more compactor storage, faster to work with. You see we have our list of points that are of the same distance. So we make 10 points. So do this step by step. So first forget about the multiplying by pi over 10 and then subtracting the pi over 2. So this is a very nice vector statement already. So we compute, so inside the function I'm importing the A range. It's already imported here. I also must import the cosine, which is vectorized. The cosine is not the cosine that we used before, the built-in cosine. It's the NumPy cosine defined over vectors. I'm also using the pi from NumPy, which is a numerical Python. So one way why this also goes so much faster is because everything is done with floating point, with the hardware floating point numbers. Okay, um, here important, and I don't think I can scroll everything so that you see. But you don't want something that is faster but then not correct. So there are two stages, by the way, to execute this. If you click on the cell and you run it, then the code will be parsed, will be translated. If there are any syntax errors in the definition, you will know it at that stage. That's why it's also important here to try statement by statement. In the second cell, then this gets executed. So here you see the execution, and we again have a 1.99999. Okay, so now the timing, is this really go faster? Did all our work really pay off? And indeed, we see we go from um, milliseconds to microseconds. And my comment is actually not entirely correct. When I ran this the first time, it was 72 milliseconds. The second time, there are fluctuations there, certainly with milliseconds. It went actually a little bit faster. But the point is, you go from, it's really different magnitude. So tremendous speed up. Okay, I may have to speed up this recording as well. And the questions now are more typical. So you will have a question about explaining things. That actually almost require no calculation, except that you can make up an example, a good example, I hope. But here you have a lot of freedom. So normal forms are important. So what is the fully factored normal form of rational polynomials? Note that I have in my answers, I have the title there. This will be question 5. Um, so I will typically not give you a hint where it is in the course. Why don't we automatically simplify and illustrate with an example? So an alternative question is, what is a good example of expressions well? And describe what is expressions well, given good example. So the fully factored normal form removes the common factors. So here you see a common factor x plus 1. It gets removed, so the denominator is just 1. The numerator simplifies to x minus 1. So actually this is an expression. Again, observe the reset. I think you have to do this with general expressions. It might not work on on polynomials over certain coefficient ring. So the example that we have seen was x to the power 1000 minus 1, which also has the root 1, and thus the factor x minus 1. But if you factor out the x minus 1, you do have expressions well. So in answering this question, you know expressions well, so you don't have to define expressions well. I think that in the context of this example, we defined expressions well. So in answering questions, explain this or that, please answer the question the question that need to be answered, and do not cut and paste everything around it. Because that also makes the exam kind of strange. Some people cut and paste everything inside the lecture. So the answers that I will be expecting will be relatively short and to the point. It's an open book exam, but do not dump in an entire lecture notebook into this answer here. And there are multiple correct answers to this, so I just gave one example. Okay, so the next question is on expression trees. And again, I do not want to drag on this pre-recording past 50 minutes. We've seen examples. I picked another example of expression tree because it is a quotient. So we divide, and the division. So if you are not very careful with looking at the operands and the operators, you will actually miss that this is defined. So the division by y square minus x is actually represented by a power with a negative 1 exponent. So there is no division here. So be careful. So I give this now on the review because often people are in a hurry on an exam and they make up the division um, as uh, an operator in a general expression. So doing this might be a little bit um, tedious. I will scroll through this, but it's very important that you understand the systematic way in which the expressions are stored as data structures. So the other thing that you will see is that the other thing I need to point out is that the negative x is actually stored as, so there is also no subtraction operator. So there's just the add operator. So if you see a negative 1, so if we see the minus x, it is stored as a multiplication. So, and you will see this, you will see this by doing the proper operands and operator. So the big goal of this exercise is that you come up with this correct expression tree. So the uh, explanation that is preceding, and also using the labeled order trees, is kind of a very structured way to draw this. But in the lecture notes, there are alternative ways to draw this. And again, it should be always in a Jupyter notebook. I will not expect. So again, so this is a good way to say this. So you cannot draw the tree on paper and take a picture with your camera and then send this to me. So this is not acceptable. So it should be, everything should be in the Jupyter notebook. Okay, I have two more questions to go. Unfortunately, the answers to these questions are rather small. So here we want to rewrite an expression, bringing things on a common denominator. If we do this without taking care of the x minus y, x plus y, then the numerator will be expanded. And that's actually another illustration of expressions well. What do? We do substitution. We shield the x plus y, x minus y from expanding. And here's another question explained. Give an example on how to prevent evaluation, prevent preventing expansion. So this would be an example, for example. So there are many alternative questions to these questions. So before you can do the substitution, you must figure out new symbols for the placeholders for these expressions. So that's another thing that you shouldn't forget. And then there are, after the substitution, you factor and then you substitute again. So this is the symbolic evaluation. Explain the difference between symbolic and numeric evaluation. Illustrate with an example, an alternative question. Okay, I'm running over time. My last question is on lexicographical order, and here I can show immediately the answer. And I hope that this was one in the last lectures that this is still fresh in memory. So I hope this review was interesting. Now, these questions are good questions to prepare for the midterm. I selected some of the topics that we did not cover in quizzes. So also I selected topics for those not so familiar with Python. So one good benefit of this course is that you would be more familiar with Python. Um, okay, I will stop the recording now. Thank you for watching.